it is an amazing time in astronomy, especially observational astronomy, because of the recent launch of the James Webb Space Telescope. So how many people watched the launch of James Webb on Christmas Day? It did, yeah. Well, for me, it nearly spoiled my Christmas dinner because I was on pins as to whether everything was going to work. But as you'll see, it's been a fantastic success, and it has a 15-year, and now it's thought to have a 15-year lifetime. And we're only 9 months in, and we're rewriting our understanding of cosmic history. This was the first image, deep image, that was put on the internet and displayed to the public, taken with the James Webb Space Telescope. There's a galactic star here in the foreground, but that's not really particularly interesting. What's interesting, firstly, is this cluster of galaxies. The objects in white here are all galaxies at the same distance. They're physically associated by their gravity in a cluster of galaxies. And then the redder objects behind, many of which are stretched and distorted, are background galaxies seen at much greater distance, whose light has been distorted and magnified by the power of this foreground cluster. So just like an optical lens, can magnify an object in the distance, like a telescope or a spyglass, so a gravitational assembly of mass, such as what you see here, can bend the light and focus it and produce these stretched and hence magnified objects that are far, far away. So it's a little bit like having a free telephoto lens in the sky. You have to steer your telescope and view through this cluster of galaxies. Now, this image was presented to the world by no other than Joe Biden. Let me just say in passing, I don't think he fully grasped the significance of what was happening in this image, but we'll forgive him for that because he had many things on his mind at that time. Now, I feel obliged in this amazingly historic place to just go back in history just a little bit. I don't want to spend too much time on history because the present is so exciting. But how did we get to this position in understanding these galaxies? And it starts with this guy here, Thomas Wright, who was a landscape gardener, lived in County Durham. And he is the first person, we think, in recorded history to grasp the concept that the Milky Way is a disk of stars. And when you look along the plane of this disk of stars, of course, they blur into one another. There's so many of them, you can't resolve them. And so you just see this beautiful stream of stars. Whereas if you look at right angles to this disk, then, of course, there are far fewer stars along the line of sight. So, he published a book in 1750, and here it is. And incidentally, you can buy a reproduction of it on Amazon if you're interested. And in it is this sketch that clearly shows that he understood the principle of a disk of stars. Now, unfortunately, he embellished this idea. Instead of just having a thin disk, he wanted to be a shell, and he had the idea that there was a supreme being at the center of this shell. So if he'd have stopped with this picture, he'd have been much more famous, perhaps, than he really became, because he lost it a little bit. Somebody who's much more like a modern-day astronomer is your hero, William Herschel, and, of course, his sister. He used star counts to sketch the structure of the Milky Way, but much more importantly, in my view, he catalogued other objects which he called nebulae, and it occurred to him that these nebulae may be external galaxies, and this is written in his article, Construction of the Heavens, where he says that some nebulae, they may be called Milky Ways. So he really grasped the idea that there were external galaxies. But of course, it was a conjecture because he couldn't measure distances. He didn't, in order to prove that they were outside the Milky Way, you'd have to measure the distance. And that really was a breakthrough of Edwin Hubble, whose name, of course, graces the Space Telescope. And Edwin Hubble estimated the distance to the Andromeda spiral, our nearest large neighbor, by finding a variable star embedded within the outskirts of this galaxy and measuring the period of this variable star. And these stars are physically pulsating. And of course, we knew about them already in the Milky Way. And the period of pulsation correlates with their true luminosity. And so if you measure the period, it's a couple of weeks, then you can get the luminosity. If you know the luminosity and you know that that's the true intrinsic luminosity of the star, then of course, if you know how bright it is on your photographic plate, then by the inverse square law, you can get the distance. And he proved in 1927 that the Andromeda spiral was outside the confines of the Milky Way. So tonight's talk is about the vastness of the universe and the fact that light travels at a fixed speed. And, you know, when we look at the sun, we see the sun as it was 8 minutes ago. That's the light travel time from the sun to the earth. When we look at the nearest star, we see it as it was 4 years ago. But the situation is transformed when we use a powerful telescope like the James Webb Space Telescope. We're able to look back in time, not 1 million years, not even 1 billion years, but over 13 billion years. Now, the universe itself is 13.8 billion years old. So that's about 3 times the age of the Earth. And, you know, when we look at objects at different distances, we therefore see directly in the past. I think it's an ancient dream that we could time travel. Everybody has their, you know, I don't know what you'd like to do. I'd like to go and see the pyramids being constructed in real time. But, you know, astronomers are time travelers. We can actually go back in time. But how do we know how far back in time we're looking? We can't measure the distances of every object that we look at. We need some marker. You know, that picture from Joe Biden has galaxies at a whole range of distances. So it's like a time tunnel. We need to somehow slice this picture into different time series and piece together the evolution of the universe. Sadly, we don't live long enough to see any galaxy change. But what we can do is study the evolution of the population. And for that, we need a marker. We need some measurement of how far back we're looking. And the trick is that the universe is expanding. Now, you've probably come across the expansion of the universe. It's incorrect to think of the expansion of the universe as projectiles moving through pre-existing space, shot out of the Big Bang. That is not the picture at all. It is space itself that is expanding. The galaxies are stationary in space, more or less. They have their own little peculiar motions, but basically they're fixed to space. And it's space itself that is being stretched. Yes, it's a difficult concept. So imagine now a light ray, a blue light ray, leaves this galaxy here and travels towards the Earth, and we're here. And this is a long way. And so as the light ray comes towards us, space is stretched, and the light ray is stretched too. And we call this the redshift. This is the only equation in my book, and it's not necessary to understand it, actually. The light ray is stretched. If we can measure the factor by which that light ray is stretched, for instance, there may be features in the spectrum from hydrogen or helium or carbon, whose laboratory wavelengths we know, then we can measure this redshift. Now, this redshift is a measure of by how much the universe has expanded since the light left that galaxy. So if we have a model of how the universe expands with time, then measuring this redshift, shown along the top here, can be converted into what the astronomers call the look-back time. It's a very important concept, how far back in time we're looking in actual billions of years. So a large redshift means a large look-back time. The universe has expanded by a large amount since the light left that galaxy. So my colleagues and I and our many competitors all over the world, it's a very competitive subject, believe me, have pieced together over the last 20 years, largely with the Hubble Space Telescope, a picture of how galaxies have evolved over about 90% of cosmic history. So here today, we see two kinds of galaxies. This galaxy is what we call an elliptical galaxy. You can see it's very simple. It's a ball of stars. They're all the same color. This galaxy is a spiral galaxy, much like our Milky Way. You can see it has spiral arms. They're blue. It has a red nucleus. This particular galaxy has a companion. If we go back to when the universe was only 5 billion years old, you can see there are galaxies that resemble the elliptical galaxy here. There are galaxies that resemble the spiral galaxies that we see locally. Maybe they're not quite as elegant. And there are irregular galaxies. We see irregular galaxies today. They don't have any symmetry, but there seem to be more of them as we go back in time. If we go to when the universe was only 1 to 2 billion years old, you can see the situation is completely different. These galaxies are physically small. Many of them have multiple components as if they're coalescing. They're still assembling. And there's very little symmetry, no spirals, no regular looking objects. So I'm not saying that we completely understand this picture, but I think this area of cosmic time from when the universe was 1 billion years old to today is rich with data. And so the challenge now, and what is feasible with James Webb, is to go back to what we call cosmic dawn. So what is cosmic dawn? It features in the title of my book. It's in the title of the lecture. This is obviously a cartoon with time running from left to right. This is the glow from the Big Bang. And as the universe expands from the Big Bang, as space is stretched, so the gas cools. There are no stars or galaxies at this time. It's just clouds of hydrogen gas. And these hydrogen clouds cool, and eventually they collapse under their gravity. They're dark, they're not shining, there's no starlight. And as they collapse under their own gravity, they get hot, just like a bicycle tire gets hot when you compress the gas, the air in the tire. And so that heat, the temperature rises enough to cause nuclear fusion, which is, of course, how the sun shines, converting hydrogen into helium. So these baby galaxies are the first signs of light in the universe. Sometimes we call this first light. And it must be an amazing moment. The question is it a dramatic event? Did the universe switch on like that? Or was it gradual? Did some stars and galaxies form slowly and then others followed, etc.? So this cosmic dawn is the beginning of chemistry, because everything that we see around us in this room is synthesized in nuclear burning in stars. Even our own bodies, the iron in our blood, the calcium in our bones, all was made in stars. The material from the Big Bang is just hydrogen and helium. And so, this cosmic dawn is ultimately the beginning of everything that we see. It's the beginning of the chemistry. Even you could say it's the beginning of our own existence. Of course, the Big Bang's important and very mysterious, but witnessing and timing this cosmic dawn is exciting and a major quest right now in astronomy. Well, it's an unfortunate fact that we live in a world with theoreticians. They have no need for observations. All they need is a computer, and they simulate cosmic dawn. So this is the time since the Big Bang. And what you see is the birth of stars. This is a zoom. This is the hydrogen gas, which is in filamentary. And as these stars are born, they live very, very quickly. Many of them are very massive. And when they end their lives, they explode as supernovae. And the processed chemistry that they've produced is expelled into the space in between galaxies. And so, you know, it's a little bit like college soup. It just keeps getting enriched, and then more of it is made and so forth. And so this search for cosmic dawn is the search for the first generation of pure stars made just of hydrogen and helium. So I like this slide very much because, it goes back to when I was an undergraduate, which was also at University College London by chance. And this is date, and this is the redshift of the most distant known published object. And this is the age of the universe that corresponds to that most distant object. So you can see when I was a young undergraduate in London, the most distant galaxy had a redshift of about 0.5. And as we've got more clever and built bigger and more powerful telescopes, we've probed to when the universe was only a fraction of its present age, 3, 4, 5% of its present age. And this story, this technological advance, bigger telescopes, charge-coupled devices as detectors, replacing photography, multi-object spectroscopy, has been the major advance that I've been very lucky to witness during my career. Even now, I was showing this slide as recently as May of last year, and it's already out of date because of the progress with James Webb. So what are these questions that James Webb is posed to address? Well, when did this cosmic dawn occur? You know, obviously it's a milestone in cosmic history. Can we pinpoint when it happened? Was it a dramatic event? And will we recognize it? Will we be able to point to a galaxy and say, galaxy has just switched on? It is a first generation system that is emerging from darkness. And the exciting thing is, you know, we've got some idea of when cosmic dawn occurred, and I'll go through that. And we're approaching that era already in the space of 6 to 9 months with the James Webb Telescope. So this was your first president, is that right, of the Herschel Society? And he's needs no introduction, but he's the guy who got me into astronomy, because when I was 6 years old in North Wales, I picked up this book, which is a story about two children, a brother and a sister, who go to visit their eccentric uncle who had a telescope. And, I realized at that point when I was 6 that that's what I wanted to do. I should say not all professional astronomers have this sort of childhood conversion. Many of them realize only in their 20s that that's what they want to do. But I was very fortunate that I knew even at the age of 6 what I wanted to do. Years later, when I appeared on his Sky at Night program, I told him this story. And when I got home, he sent me a copy of this book, which I had long lost. I mean, it was a library book, so I didn't actually have it. And it looks like it was his personal copy. So that was a very touching gesture from Patrick. So I've been fortunate over my career to use all the powerful telescopes in the world to explore the early universe. The story that I'm not going to go through in my book starts it originally starts historically, and I'll say a few words about this, at the Palomar Observatory. And as Tony said, I eventually became the director of Palomar, but the history of it goes, of course, a long way further back in time. The first British telescope that was really, how shall I say it, kicked UK astronomy into the Premier League, to put a topical topic on it, was the Anglo-Australian telescope, which is in New South Wales. And so that features very prominently in my career. And the Herschel telescope, named after William Herschel, in the Canary Islands. And then I emigrated to California and used the twin Keck telescopes in Hawaii, and then finally came back to Europe using the European Very Large Telescope in the Atacama Desert in Chile. And then space telescopes. So, of course, I was at the prime of my career when Hubble was launched. Of course, there was an embarrassing period when it was out of focus, but eventually fixed. And then there's the Spitzer infrared telescope, which has been very prominent, but now finished. And of course, the James Webb Space Telescope, which is an infrared telescope. So just say something about this idea of looking back in time. When did this quest for looking at earlier objects begin? And really it began with the Palomar telescope, and this gentleman here, George Ellery Hale, was a solar astronomer, and he was extraordinarily good at getting donors to fund an ever succeeding progression of large telescopes, for a 60-inch on Mount Wilson in California, the 100-inch Hooker telescope on Mount Wilson, and then the Palomar telescope here, which sadly he died. He never saw it to completion. When I was a boy, I had this encyclopedia when I was aged 8, and here's a picture of a cutout of the telescope. It didn't say what telescope it was, but clearly it is the 200-inch telescope on Mount Palomar. And of course, I had no idea at the time that I would eventually be the director of the Palomar telescope. Hale really recognized this idea of history going back in time. He hired Harlow Shapley, who became the head of Harvard Observatory later, but in Pasadena in California, there was Hubble and Harlow as his disciples, really. And Harlow, measured the distance to this globular cluster of stars, Messier 13. And, he realized the light travel time was 36,000 years, which by today's standards is peanuts. But in the 1920s, this was hugely important. We cannot say how the cluster appears today or whether it even existed since the dawn of our civilization. 30,000 years is as a day in the cycle of the universe. And so he realized, this is an amazing tool we have. These telescopes can look back in time. And, to raise the money for the 200-inch, he made this, this was the biggest donation ever to any scientific enterprise, not just in astronomy, but any enterprise at all in science, $6 million from the Rockefeller Foundation. And to get that money, he made this quote, "Like buried treasures, the outposts of the universe have beckoned to the adventurous from immemorial times." So Hubble was the sort of man who, was charged with looking back in time. But unfortunately, he had a heart attack almost immediately after the 200-inch came online in 1948. So although he began this program, he died, and he handed it to Alan Sandage, his disciple, who's shown here with me in Durham in the 1990s. And Sandage started looking for the more and more distant galaxies with the 200-inch. But he had a competitor in the same city. It's unbelievable. This guy, Jim Gunn, who's still alive, thought, well, I can do this project too. And I should just say in passing, sometimes people picture astronomers as, placid, wise old men with long hair, maybe going up to the telescope on in an evening and looking through the telescope through an eyepiece. Don't believe that. It's a very competitive subject. Recently, the Times had a ranking of the most stressful occupation. At the top was politician, stockbroker, surgeon, and then way down the list was astronomer, below vicar, And this is all wrong. It's a cutthroat world out there. So here are these two guys fighting to get telescope time on this unique telescope, which is the most powerful telescope in the world for 40 years to estimate, distant galaxies. Why were they doing that? They wanted to measure the rate at which the expansion of the universe was slowing down. They weren't actually interested in the galaxies. They were only interested in using the galaxies as tracers of the cosmic expansion. until a woman came along, a New Zealander, Beatrice Tinsley. And you could see, sadly, she died very young of melanoma. And she convinced both of them that the whole point of their project was futile. Galaxies change in their brightness with time. And so the subject in the 1970s, just as I was entering my career, did a huge paradigm shift from using galaxies as traces of the expansion to studying galaxies in their own interest, for their own evolution. And, you know, there was this huge technological revolution that happened just at that time. The photographic plate was replaced by the digital detector in the early 1980s, the charge-coupled device that's in your iPhone or Android, 30 times more sensitive than the photographic plate. Suddenly, like having a telescope, 30 times more powerful. Just the switch of the detector, nothing to do with increasing the size of the telescope. And now, of course, we can make mosaics of these detectors. So this is an 870 megapixel camera that allows an 8-meter telescope to take a picture of the entire Andromeda galaxy. Then, of course, bigger telescopes. They came. The Palomar was eventually eclipsed by the twin Keck telescopes, the Gemini 8-meter telescopes, the ESO 4 8-meter telescopes. An innovation here is that the telescope is made of segments. It's not a single mirror. It's 36 hexagonal mirrors, each 1.2 meters across, that are very carefully supported to make a surface that forms a continuous 10-meter telescope, as is the Spanish Grantacan telescope here. And then finally, multi-object spectroscopy. So these pioneers, Sandage and Gunn, fighting over each other on the 200-inch, were measuring the redshifts, which of course is that time marker, one by one, every galaxy one by one. Sometimes their exposures were 2 nights on one galaxy. And then along came fiber optics, the plumbing, optical plumbing that allows you to measure the spectra of 50 to 100 galaxies at once. So again, a huge revolution in surveying the distant universe. When I was in Durham, we built a robot that moved all of these fibers. So the way it works is the light is coming from here and striking the screen at right angles, and then a little prism, a right-angled prism, reflects the light into the fiber. And this robot, this electromagnet comes and picks up this little end of this fiber where there's a little button and moves it and deposits it at the position of a galaxy. So, you know, it takes a bit of time to do this. Here's another one here. This one does 400 objects. Largely as a publicity stunt, because this was done with the Anglo-Australian telescope, we arranged these fibers to be a map of Australia, to which the usual comment was, what about Tasmania? Okay, so how do we find these distant galaxies? You might think that the fainter galaxies are the most distant. Unfortunately, galaxies come in all kinds of, you know, there are feeble ones and luminous ones. And so brightness, the brightness on the sky is not a very good idea as a guide for how far away a galaxy is. But hydrogen is a pervasive gas in the universe, and hydrogen absorbs in the ultraviolet. So a distant galaxy can be seen in a red filter and a green filter, but disappears in the ultraviolet if it's very distant. And so here's a red filter, here's a green filter, and here's the ultraviolet filter. And so this absorption is not in the galaxy itself. It's actually produced largely by the gas along the line of sight. And so we can apply this technique. These are the color filters in the Hubble Space Telescope. There are violet filters, blue filters, green filters, yellow, orange, and red and infrared filters. And the color, the filter in which the galaxy disappears is an approximate redshift. You don't have to get a spectrum. You just have to image the sky in different color filters, and the most distant objects disappear as this hydrogen absorption is redshifted through these filters. So let me just do a little interlude and tell you some what it's like to use one of these big telescopes. It's pretty incredible, you know. I'm a romantic. I like to stand on a mountain, watch the sunset, and then go into the dome of a big telescope and hope to make discoveries. And for a young person building their career, it can be truly inspirational. This is one of my former students working enthusiastically at the console of the Keck telescope in Hawaii. Here's another one here. And, sometimes we make a discovery in real time, and it's very, very exciting. Unfortunately, there are cloudy nights. You fly all the way over the world to Hawaii or to the Atacama Desert, and it's cloudy. And there's no rain check. Every night is allocated to an astronomer. So if there's clouds on that night, it's just your tough luck. All that way, all that preparation for nothing. This is a cloudy night photograph. This guy, these are all former students. This guy, he's quite happy. He's just submitted his thesis. So, he doesn't have to worry about the cloud. This guy's Italian. They're just always happy. I mean, it doesn't, they never seem to be upset. And this guy looking forlorn, his thesis is going down the drain because this is the fourth cloudy night in a row, and he's got no data at all. So my job then is to buy the pizza and the wine and, try to cheer them up. And I think that's why this is slightly out of focus, actually. Anyway, so how far did we see before James Webb? So this is the deepest image we took with Hubble. It's called the ultra deep field. There was a deep field, and there was a very deep field, and there was an ultra deep field. And it's an area, this is about 1/10 the diameter of the full moon. There are about 3,000 galaxies in here. It's about 2 weeks of exposure with the Hubble Space Telescope in several filters. And the most distant galaxies, I don't know if you can see it, it's a bit difficult probably, are shown here. And I want you to focus on this one in yellow, which was the most distant one that we thought, corresponding to a redshift 11.9 object. It was a collaboration with Edinburgh University. This was when I was in California, and here we are at the Royal Observatory in Edinburgh. So that's one technique for using Hubble. Point to a not particularly interesting part of the sky, unexposed for a long time. The other technique is this bending of light that I mentioned in the very first slide. No guesses for who this guy is. He predicted that light is bent by massive objects. It was verified by Sir Arthur Eddington at Cambridge, who went on an eclipse expedition in 1919. And at the time of an eclipse, of course, you see stars close to the limb of the sun that you wouldn't be able to see otherwise. And he proved that they were not in exactly the same position as they would be if the sun wasn't in the way. In other words, their position on the sky has changed due to the deflection of the light around the rim of the sun. And this catapulted Einstein into fame in 1919. My wife recently gave me a calendar, an Einstein calendar. Every month, Einstein was doing something different. He was, riding a bicycle, or he was up against the blackboard. And by the time we got to April, I realized he only had one suit, because he was always wearing the same suit. Okay, so looking through these clusters, as we showed earlier, enables you to look very, very deep in the universe. Here's a movie, it's another simulation of how a transparent lens affects the light behind. You can see we get these distorted images. Sometimes you can get complete rings if the alignment is perfect, which occurs very rarely. But it's essentially like a free telescope. You boost the light from these distant objects. So these two techniques, pointing to a blank area and using this gravitational lensing, gave the same answer. This is the census of galaxies out to a redshift of 10, when the universe was about 5% of its present age, 500 million years, 500 million years. This is the number of galaxies per unit volume. For the aficionados, this is a logarithmic scale. So from here to here is a factor of 1,000. There are 1,000 times fewer galaxies out at this remote period of cosmic history compared to at a redshift of 3 or so when the universe is 2 billion years old. Now, there was some dispute. Some observers claim that the number is falling quite steeply here, whereas others claim that the number was declining more gradually. You can see the uncertainties are very large, and that's simply because we were at the limit of what Hubble could do. All of that is out of date in the last 6 months. There's one other trick for pinpointing when all this began. Let me just say, obviously, cosmic dawn would be where this sort of curve finally, reaches an insignificant number of galaxies. So obviously, the difference between this gradual decline and this steep decline has a big impact on when cosmic dawn might have happened. There is one other trick, and that is, although we can't see to cosmic dawn with Hubble, it just doesn't have enough power and doesn't extend far enough into the infrared, we can measure the age. If we could measure the age of some galaxies, then, maybe we can get an estimate of when cosmic dawn occurred. The analogy here is you walk down the street and you meet a small boy. You weren't present at the birth of that boy, but if you could figure out how old he was, then of course you can predict when he was born. So here's a galaxy whose redshift is about 9 or so, seen when the universe is 500 million years old. Can we estimate how old the stars are in that galaxy? And there's a trick that allows us to measure the age of stars by hydrogen absorption in the atmospheres of stars, which is a well understood method that's applied in the Milky Way. And so we did this using the telescopes in the Atacama Desert. This is now when I arrived in London. And we estimated the age of this galaxy, even at this early time, was already 290 million years old. And so we estimated that it formed at a redshift of 15, which Hubble couldn't see directly, but we're making an indirect prediction. So here we are at the European Very Large Telescope. It's almost like a religious experience to go to one of these places. Look at the size of these 4 telescopes. The Europeans really know how to live. This is the only observatory with a swimming pool. And we measured the ages of 6 galaxies via this technique. And we made a bold prediction that cosmic dawn was somewhere in this redshift range, 11 to 16, when the universe was 250 to 400 million years old. And this was just before the launch of James Webb. And so it was a prediction. And the exciting thing is that that window in time was exactly where James Webb would be powerful. So finally, we get to this monster. So just before the pandemic, in fact, in January and February 2020, I was in Pasadena giving a lecture, and I was privileged to go to El Segundo, where Northrop Grumman's aerospace business is, and allowed in to see the James Webb Space Telescope. There's a human here. Give you some idea of the scale of this monster. It's got 16 segments. It's a segmented telescope. It's obviously folded up so that it can be placed in the nose cone of an Ariane rocket. It's a 6.5 meter telescope, so that's about 3 times the diameter of Hubble. So it's almost an order of magnitude, 10 times more powerful than Hubble, but also it goes further into the infrared. I was the only European on the committee in 1996 that made the case for this telescope. So 1996 to 2021. Imagine all those engineers working on James Webb for that 25 years You know, Tony mentioned I lived in Durham. You know, when you look at Durham Cathedral, entire stonemason families came from Europe to build Durham Cathedral. They lived there. You know, it wasn't the kind of thing they did in a few years. They lived there. Their children carried the tradition. So it was a generational thing to build these massive cathedrals. And this is, in a sense, a cathedral, isn't it? It's a project that took 25 years. And of course, it's been a great success. So very expensive, $10 billion, better be worth it. And, you know, imagine how nervous they are. Here it is hanging from a hook. I mean, my gosh, you know, talk about pits in your stomach. Here it is placed in the nose cone of this Ariane rocket, launched on Christmas Day. And here's our last view of it. Not serviceable. Unlike Hubble, it doesn't orbit the Earth. It orbits the sun. Can't visit it. And all this sequence of unfolding as it goes out to a point well beyond the moon, which is called the Lagrangian point. Very, very briefly, what that is the place where the combined gravity of the Earth and the sun equals the gravity that the Earth feels from the sun alone. And what that means is that the Earth and James Webb are going around the sun with the same period, because the gravity they feel is the same. And that means, of course, that, you know, we're always 1.5 million kilometers from James Webb, so the, you know, communications are more or less instantaneous. So, whoops, these slides have been damaged, I'm afraid, in converting to the other laptop. So the data is not on these slides. What a shame. That's a great pity. Well, I'll have to improvise. So you'll remember that figure. Let's go back to this figure here. And there was some dispute as to whether the numbers were declining steeply or declining more gradually. And the answer is, and I'll have to tell you because it's for some reason, it's in the conversion from the Mac to this computer, the data has been eliminated. The data is up here. We're seeing out to redshifts of 14. There may be objects even further. Clearly, and the data is up here, whereas the theory was going down here. Yeah, all the data has been, for some reason, eliminated. That's a great tragedy. The galaxies are actually remarkably bright, and this is a puzzle to us. We don't know why these galaxies are so bright. There are various ideas, and hopefully we can have some discussion on that. Another puzzle was that some astronomers believe that the galaxies are more massive than can be accounted for by the time that's available from the Big Bang. But this result has been disputed very heavily in the literature, and most people don't believe that these masses are correct. Now, I told you that all of these objects up to date had been determined by their colors. Remember that movie where the galaxies drop out in different filters? Ultimately, we need to get the spectrum of a galaxy to be absolutely sure that these galaxies are truly at these distances. Here's that galaxy that we found in Hubble at 11.9. Here's the spectrum from James Webb. James Webb is the first big telescope in space that has a very high quality spectrograph. And here's that hydrogen signal, very precisely at 11.6. We said it was 11.9 plus or minus 0.3, so that's pretty good news. We were right on that one. Basically, this redshift that's estimated from the colors is correlated here with the redshift from the spectra. And you can see most of the objects are pretty good. So, you know, they agree very, very well. we're beginning to get chemistry at these early times. So I told you that hydrogen is burning to helium in stars. Helium then burns to carbon. Carbon and oxygen burns to silicon. Silicon burns to iron and nickel. And so all of these elements are, of course, produced in stars and then expelled into space. So ideally, we can measure the composition of these early galaxies. So this, I never thought I'd live to see this. This is a galaxy right at the edge of what was possible to detect with Hubble. And here's a spectrum where we see features of nitrogen, helium, carbon, magnesium, oxygen, neon, and hydrogen. And so we really have the capability of tracing the evolution of chemistry with James Webb. And that's going to be the clue that gets us back to, you know, this chemically pristine galaxy that we would imagine to see at cosmic dawn. So that's more or less the end of the talk. I just say that the key signature of these early galaxies will be that they will only have the elements that are made in the Big Bang, hydrogen and helium. It will be challenging. It's not like we're going to wake up one day and say, oh, we found a galaxy. You know, we would like to do this statistically with a population of galaxies. So, you know, it's going to be challenging. But we have this fantastic telescope now for at least a decade. Originally, it was to be 5 years with a goal of 10 years. And now it looks feasible that it'll be up there for working for at least 10 years, maybe 15 years. And even though there are challenges, you know, when I look back over my career at all the big telescopes, they each of them achieved much more than, you know, the science that they were predicted to do. I like to say, unlike politicians, astronomers deliver far more than they predicted. Thank you very much.
We'll start off with questions. We'll start off with questions in the room, and then I'll look to see if there are any on the chat channel.
Can we turn the lights up so we can all see each other?
Anyone with a question in the room?
Okay. Good evening. Thank you very much for your talk. It was really fascinating. I have a question which might be a really simple question for people who know about astronomy. I'm not an astronomer professionally. But I wanted to ask, if we could construct more powerful instruments that could see further, would it actually be possible to see the Big Bang?
No, well, okay, so the question is, you know, can we see the Big Bang? And the answer is we can see the glow from the Big Bang, and it was seen in 1965 by accident. The glow from the Big Bang, if we could imagine going to as close as we can get to the Big Bang, which is about 370,000 years after where the hydrogen atom forms, and the radiation from the glow from the Big Bang can travel in a straight line. It would be glowing in the optical, in something like an orange light. But because the universe has expanded over 1,000 times since then, that orange light is seen at millimeter and radio wavelengths. And so in 1965, two astronomers accidentally discovered this radio signal from the sky, which is everywhere, all around, isotropic in the sky. And its temperature matched what was predicted from the glow from the Big Bang. Can we look any further back than that? I mean, in principle, if we could make a neutrino telescope, a telescope that could detect the signal from neutrinos, we could actually go back to when the universe was even younger. But that's several decades away to have the sensitivity to do that. Turning back to cosmic dawn, we could certainly look further back than cosmic dawn and see the beginning of structure. These dark hydrogen clouds can be detected at radio wavelengths. And so next decade, there will be a very powerful radio telescope called the Square Kilometre Array, which will have the sensitivity to go into the dark, what we call the dark ages. Astronomers are very fond of that word. The period when the universe was dark, but there are hydrogen clouds. And those hydrogen clouds are, although they're cold, they do radiate, and they both radiate and absorb at radio wavelengths. But in terms of starlight, cosmic dawn is the furthest we will see. There's a question over here, I think. Oh, right. Well, whatever's more convenient for you.
Thank you. I apologize. This is a really lay question, but how do you personally conceptualize the time before Big Bang?
That's a new question. I've never heard that one before. Okay, so I know it may not be a satisfactory answer, but if you can imagine space compressed to a point so that space has a beginning, then if you could imagine that time is intimately connected with space, then time can have a beginning too. Now, I know that that's difficult to imagine, but if you can get your head around the idea that the universe came into existence from a point, so that space didn't exist until the universe began, then maybe you can make that, conceptual leap to the idea that time is nothing different from space, and time begins when the Big Bang occurred as well. There is no answer. We don't understand the Big Bang. We don't understand the physics in the early fractions of a second. There are tools that we can develop to try to understand this, which relates to the earlier question. These signals from the glow from the Big Bang do contain information about what happened before that surfaced, where we can see the radiation for the first time. But it's an interesting area of physics that's still very, very poorly known. I told you wouldn't like the answer.
Right, there was someone over here. Probably slightly related questions, but firstly, what was the mechanism that took you from the Big Bang to the clouds of hydrogen and helium forming? And then secondly, you said the clouds have this sort of filament structure.
Yeah.
Or at least computer simulation said that.
Yeah.
What would lead to the filament structure versus some sort of uniform structure?
Okay, it's called cold dark matter, is the short answer, and it's basically that what we see in the universe is obviously starlight and stuff that makes up you and me, gas, dust, elements, and so forth. But there's a minor fraction of the material in the universe. The rest of it is dark. We don't know what the dark matter is, but we know where it is and we know how much there is. One way of measuring how much dark matter there is this this gravitational lensing, the bending of light by that Joe Biden cluster is inconsistent with the shining galaxies. There's far more mass in that cluster than can be accounted for by the individual galaxies that are shining. So we know this dark matter is there. We don't quite know what it is. The hypothesis is that this dark matter is a particle that fractionates out of the Big Bang on its own before the glow from the Big Bang that we see 370,000 years later. So this dark matter is already clumped. And when the hydrogen atom forms at 370,000 years after the Big Bang, then the gas clouds are drawn into this filamentary structure that is a feature of this cold dark matter. So these simulations are all based on the idea that this dark matter is a particle, and the calculations in these simulations are all based on this. Now, you may say, why believe it at all? And the answer is that if you run these simulations to the present day universe, it can explain the distribution of galaxies incredibly well on many scales, on small scales and on big scales. And if the dark matter wasn't there, if you switched off the dark matter, we wouldn't be here today, where the Milky Way wouldn't have had time to assemble. So the only way that we see these galaxies around us today is if these simulations are correct. So it's a bit of an edifice, and there have been many people, believe me, over this picture is now 20 years, well, over than that, maybe 30 years old now. And many people have been chipping away at it, trying to falsify it. And it stood the test of time remarkably well. It's what we call the standard model. And of course, everybody would love to demolish the standard model, but it's held up remarkably well. But it won't be verified until we know what the dark matter particle is. And that's really not the job of the astronomer. It's really the job of the particle physicist. Right, these are all very profound questions.
We have some questions on the chat channel. I'll come back to the room in a minute. We have Richard Stableford asked rather a big question. At the end of its 15-year mission, what questions will the JWST have answered, or at least given us clues to?
Yeah, well, let me first say that you've heard today one theme of what James Webb is doing. I haven't talked at all about exoplanets, haven't talked about the solar system. It is a general purpose observatory. The story I've given you today is about one very small area of astrophysics that James Webb is well suited to do. Of course, I personally think it's the most exciting and interesting, but, there are astronomers working in all of these other areas at all. The other it would take a long time to explain all of the achievements that James Webb might accomplish. I'll just say two things. One is that the search for Earth-like planets was one of the pillars in that report in 1996 that I was on. And so that search for characterizing the atmospheres of Earth-like planets to search for biosignatures is one big goal of the James Webb Space Telescope. But the other thing I'd say is more general, that all of these telescopes have discovered things that we didn't foresee. And in some sense, it's those unpredicted discoveries that really shape science. So, for instance, if you go and look at the history of what Hubble and the Keck telescopes were supposed to do, they did not predict that we would find that the universe is accelerating, which is a big mystery that we still don't completely understand. So I think the most exciting thing is not, we're just ticking the boxes of what James Webb should have done. It's largely that with all science, it's finding the unexpected that's really the exciting thing.
Now, Richard B., this is another Richard, he asks, what sort of instrument do you think may replace JWST at the end of its life? Okay,
so that's a fairly straightforward question. Obviously, every 10 years or so, there are plans, particularly in the United States, but in Europe too. Committees are set up to brainstorm what should happen. If James Webb took 25 years to reach launch from its conception, then we better start planning for whatever's coming next. So one of the areas that is being discussed right now is a replacement for Hubble. So you may think James Webb is a replacement to Hubble. That's not strictly true, because James Webb is an infrared telescope that was sensitive to these galaxies at great distances, whereas Hubble is an optical, an ultraviolet telescope. Now, there's a lot of very important astrophysics that we don't understand that can be addressed with a bigger version of Hubble. So there was a big survey of astronomers in 2020 called the Decadal Survey, and a 10-meter or 12-meter space telescope operating in the ultraviolet and optical is one of the themes that's come out of that. It's not funded yet. It would be very expensive. But that's one of the areas that likely would develop in 2040 or so. On the ground, this whole idea of these robots is gaining momentum so that we can chart the distribution of galaxies on very large scales, which would address some of these questions about dark matter. And so right now, in fact, I'm involved in a project that is looking to build a telescope that would be able to survey 20,000 galaxies simultaneously. That's a project that's likely to happen in Europe in the next 15 years or so as well. Now, all of this, of course, depends on continued budgets and excitement and good results from the facilities we have. Well, the good news is, of course, James Webb is great news at the moment. Everybody's excited how productive it is. So hopefully that encourages, the governments to keep funding astronomy.
Right. I have another two questions from the chat channel. I'll deal with them and then we'll come back to the room. So Paul Richardson asks, is there any explanation for the earliest galaxies seen by the JWST being brighter and possibly more massive than expected?
Yes.
Or is the observation incorrect in some way?
Yeah, thank you. Yeah, I'm sorry that those slides didn't come out well, and I'm happy to bring out my laptop and show them to anybody in the room afterwards if there are questions. The results look correct because although these color-based redshifts are approximate, as we get more and more spectra, it's looking like the technique works and the redshifts are correct, as I showed. So I think these objects really are at these great distances. Their brightnesses are easy to measure, thanks to the power of James Webb. So the results are, I think, correct. So what could it be? Well, it looks like when the universe was very young, that these galaxies form more efficiently. Their stars can form more efficiently from the gas than they do later. And that may be due to one or two reasons. It could be that most of the light is coming from massive stars. Now, today, if I take a gas cloud and I convert it into stars, there's something called the mass function, which is the distribution of the masses of those stars. I don't know if you're aware that the sun is a fairly typical star, but there are massive stars, up to 50 times the mass of the sun, and there are feeble stars, a tenth of the mass of the sun. So a gas cloud somehow knows to fragment into this distribution of feeble stars and massive stars. But the hypothesis is that when the universe is very young and the gas cloud is free of these heavy elements, it's skewed to more massive stars, which are luminous, short-lived, and therefore very, very bright. And that would explain why these galaxies at early times are much more luminous than we expected them to be. There are other reasons. One is that they don't have any dust. So dust is a material that absorbs starlight. And if the universe is free of dust, then, of course, the galaxies will be brighter than we would expect them to be. So there's a lot of head scratching at the moment. You're right up to date because, this result of these bright galaxies being too bright is only from about Christmas. And, so conferences that I've been to in Italy in March, we were spending a whole day trying to head scratch and think what this may mean. And we're not there yet, but the data is coming in every day. And so hopefully we can test whether some of these ideas are the correct.
Right, a different kind of question from Judy. She asks, your slide is entitled The Holy Grail. Is there any room for religion in this story?
Oh, yes, of course there is. Well, every astronomer will have a different answer to this question. So it's just like society at large today. I was brought up religiously. I sort of like to imagine that the universe has a purpose. You can turn that into whatever statement about God that you would like to make. But certainly it is an amazing universe, and we're just very, very privileged that we have the capability to explore it, not just locally, but in its history as well. And, we've touched on some of these grand questions about the Big Bang, and hopefully I've explained to you that cosmic dawn is just as important as the Big Bang. If you can remember one thing from tonight, the Big Bang isn't the whole thing. There's more to the universe than the Big Bang. Cosmic dawn is just as important.
This is definitely another lay question from a non-specialist, but one of the things that puzzles me in hearing this discussion, if you're thinking about light that came from ever longer ago,
yeah,
the further it's come,
yeah,
the closer it is, in my head, the closer it is to the location of the. You never talk about direction, but if you think of it as being an expansion, then you have to be looking in the right direction to see the light's coming from where it was, very shortly after the Big Bang.
Yes,
so
yes.
Is it close to the Big Bang? So do you have to look in the right direction to see the Big Bang?
No.
But is that a confusion about the concept of space?
Space is stretching in all directions. So there's no, sometimes people say, can you point on the sky where the Big Bang was? It's not as simple as that. The space is stretching isotropically in all directions. So the universe is expanding uniformly. So every object sees every other object moving away. We're not special, when objects are moving away from us. If we could magically transport ourselves to another galaxy, we'd find exactly the same thing. Everything would be moving away from us. The light ray is traveling on top of the expansion of the universe. So it's stretched too, hence the redshift. These objects that we're seeing with James Webb and Hubble, they don't exist today. Okay, we're seeing them as they were in the past. Just like if we, ran a movie of, go back and look at all these black and white movies from the 1920s. Those people are no longer here. And so it's exactly the same analogy.
Yeah, I mean, I understand that they may no longer be here, but the point is you're seeing the light.
Well, they're in the same universe, okay? But
yeah.
The universe was compressed at that time. So in terms of geography, you can't predict where they would have been in the context of the geography of the universe today, because the universe today is so much bigger.
Right. Okay.
We'll keep at it. Yeah.
So, Richard, do you think it's helpful to use the surface of a balloon analogy then?
Yeah. Carry on.
So,
yeah.
well, I'm not going to do that.
As we learn more about the cosmic dawn, does it also teach us about the future of the universe?
No. This discovery of the universe speeding up, which I mentioned as a big surprise, which got the Nobel Prize in 2011, was unforeseen. And this acceleration of the universe only kicked in about 7 billion years ago. So the universe that we're looking at with cosmic dawn is relatively simple. It's expanding for sure, and it's slowing down because the universe has gravity. But then mysteriously, when the universe was about 7 billion years ago, something kicked in. As the density of the universe went down, this mysterious dark energy took over and started the universe to accelerate. And so it's a very depressing universe, because as the universe ages, it's speeding up its expansion. Galaxies get further away from one another. The universe gets darker, and eventually, of course, the stars. I mean, there's only so much hydrogen in the universe that's being converted into stars. And in fact, the universe is in decline. In terms of forming stars, the universe went through its sort of peak. You've heard of cosmic dawn. Well, astronomers also have a phrase, cosmic noon, which is when the universe was at its most energetic stage in forming stars. And that was when the universe was about 3 billion years old. And I'm sorry to say, it's downhill all the way since then. It's, I try not to get worried about it, but we're running out of gas. And so, unless there's some aspect to this acceleration that switches off in the future is pretty grim. I'm sorry to spoil your weekend, but several questions in the front. This guy's been waiting a long time.
Oh, okay.
If we go back to slide 1 with Joe Biden.
Yeah.
You said that the microlensing image part of the images were due to the mass of the central cluster.
Right.
But there do seem to be a few microlensing images that have a center which is not the center of the cluster.
Right.
So are there multiple centers for the lensing process?
A cluster is not, unlike lensing by a star, which is a point, the cluster is an amorphous object with lots of lumps and bumps where the galaxies are. And so there's a huge industry in astronomy right now to take those clusters and make a map of their lensing capability directly. And it's quite complicated machinery. So yes, you're right. It's much more complicated than microlensing.
Is there an edge to the universe?
No. The universe is infinite. So you know, and space is flat. So you can keep going, and you won't fall off the edge or anything.
Just after the Big Bang, there was inflation. Why did inflation happen?
Well, it's a theory, you know, and I'm not an early universe person, but theory, there's the argument for inflation is that the universe had a very rapid period of expansion very, very early on, and that is needed to smooth out the universe so that it's more or less the same in all directions and uniform and so forth. Believe me, there are many different types of inflation. There's, you know, it's not like there is a theory of inflation because it's poorly constrained. The way we could test inflation is to look at the structure in the glow from the Big Bang in exquisite detail. So this has been done to some extent by satellites, but now there are experiments in Antarctica, where of course it's very cold, that aim to measure what we call the higher order moments of the signal in the glow from the Big Bang. And the hope is that those measurements, which are not yet underway, will enable us to test these different models of inflation. At the moment, inflation is a theory. Most people are intrigued by it, but not everybody buys it.
You mentioned dark energy. Have any of the results from JWST helped throw any light on the theories?
No, dark energy, as I explained, is a late feature of the universe. It's best to address dark energy with gigantic surveys over large areas of sky where you have huge statistics of the distribution of galaxies and their motions and so on. James Webb is not designed to do that. James Webb has a small field of view. It's very good for very deep studies of, you know, small areas of sky. So it's not an appropriate tool. So the projects that I mentioned in answer to the question of what comes next after James Webb, many of those projects are aimed to address the question of dark energy.
Yeah, I was just wondering what your thoughts on the end of the universe were, since you mentioned space being infinite, like whether you think we'll have a big crunch or like a steady state mode.
Well, steady state was ruled out a long time ago with 3 observations. One, that we see the glow from the Big Bang, the chemistry that is produced in the Big Bang, hydrogen and helium, match what we observe. Big crunch would require the universe to collapse again. And as I described in my depressing weekend story, you know, the universe is not heading that way unless there's something that we don't understand about dark energy. So we live in a universe that's expanding and will continue to expand forever, as far as we can see at the moment.
Right. That looks like an end to the questions then. I'll just check the chat, Carol. Yeah. So that ends the lecture for tonight then. And I must say, I'm going to take some time to digest all this. It's a lot of information, but I'm particularly impressed by the latest comment on the very early galaxies, how they were how they are believed to be more luminous because they're forming stars more efficiently, being made up mostly of hydrogen and helium, and that seems to be an entirely new result.
It is indeed, and it's telling us we're very close to cosmic dawn, I think.
So let's thank Richard Ellis for such a great evening.